Okay, I'm going to end the poll. Okay, let's see. Share the results. Are you guys able to see the results? Yeah. Okay. So let's see. The first question. Which of the following statements about density matrix is always true? Most of you answered it correctly. So trace of row, excuse me, trace of row must always be 1 because the total probability is 1, and all eigenvalues must be non-negative. So that's the only statement that's always true. The remaining things could be true, but they're not always true, right? And so people, I see 2, 3, 4, 5 people answered it incorrectly. So please go back through the slides and make sure you understand. And if you have any questions, you could put them here. What is the main reason we use density matrices? It is because we want to do the averaging. So there was also a question that was raised about convex combinations. So when we are talking about convex combinations, we're talking about adding with probabilities directly, not probability amplitudes. So when I say, for example, let's say I say state vector psi is equal to alpha times 0 plus beta times 1, let us say. Right here, alpha and beta, they're not probabilities, they're probability amplitudes, meaning that I need to square them, right? If I do alpha star alpha or beta star beta, that's what is the probability. And that is why I cannot average the state vectors, because I cannot add probability amplitudes, right? I mean, I can add probability amplitudes, but then it will give me invalid state vectors. Like I can do psi and minus psi, just by adding a phase, it would just give me a 0 state vector, right? So a convex combination means that we are using probabilities directly. So when I say rho, a density matrix, is equal to P0 rho 0 plus P1 rho 1, so on and so forth, Pk rho k. That means this P0, P1, Pk, they are all probabilities, right? It's always the probabilities will add up to 1. But here the probability amplitudes do not add up to 1. So if I add alpha plus beta, this need not be equal to 1. In fact, it could also be complex, right? So it does not, alpha plus beta itself does not have any meaning. What is meaningful is alpha square plus beta square, which must be equal to 1, right? So this is not really a convex combination. Whereas here, when we are adding the density matrices, we're directly multiplying with probabilities and not probability amplitudes. So if I did something like sum over k, pk, then that should be equal to 1, right? So all the weights, each weight is a non-negative number between 0 and 1. And when I sum all those weights, I would get 1. So that's a convex combination. Whereas here, these things, alpha and beta, are complex numbers, could be complex numbers. So they are not really weights in the same sense. So that's just a comment on the convex combinations. Okay, let's see here. Third question, if you have a bipartite system, right, you have 1 cross 2, then the reduced density operator for subsystem 1, to obtain that, you have to sum over system 2. This is again has to do with our probability uh, probability like if I have joint probability like P of xy and I just want to get P of x, then I sum over all the probabilities. Uh, I just do sigma P of xy. Am I making sense? Are there any questions? So taking trace over the partial subsystem 2 is correct answer. So a lot of you answered multiplying row by identity on subsystem 2, which is not correct. We have to sum it, and projecting onto state 0 is also not the right answer. So please check that. Okay, so this one, why is it necessary to measure a qubit? I think most of you answered correctly. No, because measuring in multiple paces doesn't increase the number of qubits. Whoever answered that, I wish it was like that, but it is not. Here, fifth question. So all of the above is the right answer. So I cannot say that people who answered those choices 1 and 3 are wrong. They're partially right, but all three are different options. The first option is a single measurement. So single measurement cannot give you the state, obviously. Then even if you repeat the measurements in Z basis, you can get only expectation value of Z. You cannot get X and Y. So, but the probabilities must encode all the bases. So that's the point there. Can you explain the question third again? Third question. Okay, sure. Yeah, so if you have a density matrix, right, where we have row one, some system, and row two, right, it is just like saying I have probability, joint probability. So we basically sum over all the possibilities, right? So if you just, if you remember joint probabilities, if I want to get probabilities of only X, you sum over all the probabilities of Y, meaning that um, for example, if I say what is the probability that X is wearing a green shirt, and Y is wearing, some other color shirt, right? Then you sum over all the possibilities of Y because you want to remove Y, right? So irrespective of what color shirt Y wears, you just take only X. So you sum over all the possibilities of Y to remove that. And so you get only probability of X. In a similar way, you sum over all the probabilities of 2 so that you have only the first system. I hope that makes sense. Okay. Any other questions? Okay. Um, I think the convex combination, Subhanshu, I think you asked that question. Did that answer your question? Can I say convex combination is a way to represent a general state as a linear combination of density and matrices? Yes, you could. Yeah. The only thing, the difference is you're multiplying with probabilities and not probability amplitudes. That's the main thing. So that's the main thing for convex combination. That you're multiplying with probabilities which are non-negative and they add up to 1. Okay. Okay, then let's proceed to discussing today whatever we have left from yesterday, and then I want to get into. So today, after finishing this slide, the density matrices, I think will complete whatever background quantum mechanics we need. So let's get to, we talked about reduced states, but in general, we want to talk about correlation. So let us see what is uncorrelated states. So whenever we talk about two systems that are combined, right, if we can separate them, if we can express them by factorizing like this, row one and row two, if I can separately express them, they are separable, then we say that they are uncorrelated, right? So that means that if I make some measurements on the first qubit, and if I make some measurements on the second qubit, I do not see any correlation in those things. The second system is independent of the first system, so we can factorize them and express them as a separate state. So if I can express like this, then we say that they are uncorrelated, right? So we can classify states based on whether they are pure or not pure, and then come up with whether the total state is pure or not pure, and then we can see whether that state is mixed or not mixed. Again, to recall, when we wrote about rho, right? When we have rho, trace of rho is always one, right? No matter what. Whether it is a mixed state, pure state, doesn't matter. Trace of rho is always one. But if trace of rho square is 1, then that's what we called as a pure state, right? And if trace of rho square is less than 1, and the other side is 1 over d, right? If it is less than 1, we have a mixed state. But if the trace of rho square is equal to 1 over d, where d is the dimensionality of the system, that is, if I have a qubit, the dimensionality is 2. If I have a qubit, then I have dimensionality of 3. Quartet, then that's dimensionality is 4, right? So if for a qubit, if trace of rho square is half, then we say that's a maximally mixed state. So in fact, we saw that if I have two orthogonal states, then I saw that we saw that rho would simply come out to be I by 2 always, irrespective of what state that was. We discussed this yesterday. So is the difference between pure state and mixed state clear? Any questions on pure and mixed states? So if we, okay. Okay, Priyanshu, you haven't found the proof for this equation. Okay, I will try to find where it is. Could you give an example physically to get an intuitive idea? Okay, we discussed that kind of yesterday. So let me go back to that example. And it was not clear to a couple of you. So then let's go back to this example here. Okay, so let's say I write some state like psi, right, is equal to alpha 0 plus beta 1, right? Now, if I want to compute the density matrix for this, what I have is psi, right? And that is nothing but alpha beta and alpha star beta star, right? So that gives me alpha star alpha, beta star beta, alpha beta star, alpha star beta, right? So this is nothing but alpha square, alpha beta star beta, beta square. So if I take the trace of rho, that is alpha square plus beta square, and it is always 1 because we require that probability to be 1, right? So that is always satisfied irrespective of which state you have. But if I want to look at rho square, right? If I want to look at rho square, then I need to do alpha square, alpha beta star beta, beta square, right? Again, same thing, alpha square, alpha beta star beta, beta square. And then if you do the math, you will see that the diagonal elements will come out to be alpha square times alpha square, alpha to the power 4 plus alpha uh, uh, beta star. So you just basically get 2 um, 2 or 1 alpha square beta square, and then you could do the off diagonal elements. For the diagonal elements, if I do this, I would get beta to the power 4 plus again alpha square plus beta square. It doesn't matter what the off diagonal are, because I just want to calculate the trace of rho square. And we saw that if I did that, I get alpha to the power 4 plus beta to the power 4, 2 alpha square beta square, which is nothing but alpha square plus beta square whole to the power square. But this is 1. So I get 1 square, which is 1. So trace of rho square is also equal to 1. Not just trace of rho, but trace of rho square is also 1. So then this is a pure state. Does that make sense?
Yes, sir. But I was trying to get a more intuitive idea about mixed states, actually.
So, I mean, mixed state is basically where you cannot express like this, like a linear combination. So here, pure states you can express as a linear combination of states in terms of the state vector, meaning like I can do alpha 0 plus beta 1. But let's say in terms of quantum computation, right, I make a qubit or I prepare some system, right, it is coupled with environmental noise. There is some decoherence. that cannot be captured in the linear combination of alpha 0 plus beta 1. So then you get off diagonal elements that are not captured, and or you get other things that cannot be expressed like how I am expressing here as psi. So to talk about those, we talk about mixed states. Does that give you the physical example? Okay. Okay. Anuradha, did that answer your question? Okay. Okay. So, and Priyanshu, I'll try to find the full proof for you. And um, no, not necessarily entanglement. We'll get to entanglement in a minute, Saptagiri, and then we will see what entanglement is. Okay, so if we have a state like this, like plus and minus, each with probability half. So I'm not mixing. So when I'm doing the density matrices, I'm adding the probabilities themselves. So I can get this kind of maximally mixed states that I cannot express. Like for example, if you take this matrix, this density matrix, and try to express that as a linear combination, right? That so for example, if I express this, what you're seeing here as plus and minus, or even I think I had one with yeah, like this state 0 and 1, right? I cannot express this like alpha times 0 plus beta times 1. Are you with me? So that's why that is a mixed state, because here we are adding probability amplitudes. So because we're adding probability amplitudes, that's a different way of combining. And so we are using density matrices that would allow us to make convex combinations, meaning I can multiply with probabilities. So that is the difference. That's how we can get mixed states. That need You may not be able to express these states like what you have here, half 0 0 plus half 1 1, in terms of what you have as psi here, like alpha 0 plus beta 1. Okay. So you can have a mixed state even for like a single particle, single qubit. So when we talk about an entangled state, you need, like, it is entanglement is between two things. Like you usually have two electrons that are entangled, or two qubits that are entangled, but you could have just one qubit that I can prepare in a mixed state. That is not necessarily, I wouldn't say, is entangled, right? I hope that answers your question, Saptagiri. So we talked about all this yesterday, and yes, okay, great. So let's get to the table that I had, right? So if both states are pure, that is, if I have both states where trace of rho square is 1, right? And you combine, you make, so we're talking about a system where we have rho 1 and rho 2, right? Two different, let me not put it in the superscript like that. Rho 1 and rho 2, right? So if rho 1 is pure and rho 2 is pure, right, the total state is always pure. That is, if you have, because by the definition, right, of trace of AB, right, you can see that trace of rho square will always be 1 here. So if you the states are pure, total state is pure, right? And if one state is pure, another state is not pure, then you get a non-pure state. But if you have two non-pure states, you can use two non-pure states to make a pure state. That is, so you want trace of rho square to be 1, right? So you can use two non-pure states you can use two mixed states to come up with a pure state, right? So we will see how that comes up, right? So if rho 1 is pure, rho 2 is pure, rho is pure. But this doesn't mean that they are correlated. So they are always uncorrelated. That means both are pure states, they're separable, they're independent, and so there are no correlations. if one state is pure and the other state is non-pure, the total state that results is also not pure. They're still not correlated. That is, whenever I am talking about correlations, what I'm meaning is we have two qubits or two things. I make measurement on one and I make measurement on the other, repeated measurements. These repeated measurements would show some correlations. If they show some correlations, that's what I say is correlated. Whatever observable I measure. So I measure, let us say, I have two qubits, I measure spin along z direction on first qubit, I measure spin along the z direction on second qubit. So when I say measure, I'm making multiple shots, not single shot measurements. I'm making multiple shot measurements on both sides. And if I see that after multiple shots, there is some correlation, that is, whenever I find this is up, this is down, right? And whenever I find this is down, this is up, not on single measurements, but overall statistical correlations, multiple measurements. I make 4,000 shots, right? And for 2,000 times, I found that this is spin up. Then if I find 2,000 times on the right-hand side that it is spin down, then I would say that that is correlated, right? Again, we're talking about statistics, not single measurements. Be very careful there. Not single measurements, statistics, right? So if I have one pure state and another non-pure state, they need not be correlated. So they're always uncorrelated. The only ones where we have correlations are both non-pure. Both are mixed states, then I can get correlations. If both are non-pure states, I can get either correlations or no correlations. I will show you examples. But the drive home message here is if you have at least one pure state, then you do not get correlations. So if rho 1 or rho 2 is pure, then you do not get correlations. They're always uncorrelated. To get correlations, you need both non-pure states. You both need mixed states, right? Again, when we are talking about correlations, there must be two qubits. These correlations are related to entanglement. In fact, what people mean by entanglement is that there are correlations among observables. And when we talk about correlations, we're talking about correlations between two things. So you may hear stuff like the electron is entangled with itself. That I do not know what that means really. Because when I talk about correlations, they're between two different qubits or two different things. So we have two different systems, or you can also have multiple systems, but you have n more than one, right? Is that clear? Any questions? Okay. So let's say take pure states right here. So let's say rho of one, right? Let's say rho of one is related to some state phi, right? And rho of two is related to some state psi, right? So then I can make a mixed system, right? Then you can show that the trace of rho square, right, would be simply be one because these are two are independent. So my phi would be separable, right? So I can make this phi tensor product with psi, right? Is same as saying if I have phi tensor product with psi, right? Phi tensor product with psi, right? Then the first one multiplies the first one, right? So you get phi, right? And the second one multiplies the second one, so you get psi, right? So I can express these states as separate mixtures, right? So they are pure and uncorrelated. Are you with me? So if both states are pure, then you can express the total combination as phi tensor product psi, right? And then I can get this state by simply taking the tensor product over those two things, right? So I can then express, if I call this as another big phi, then I can express the total as big phi, right? So then that looks like a pure state. Are you able to see that? Are you with me? Any questions? Should we know the basics of tensors? There is no tensors here. It is just the tensor product we are taking, and I think like there is the code that I put yesterday. there we saw that if I have like a 2 by 2 row 1 and 2 by 2 row 2, we were just repeating that matrix 4 times. So you get a 4 by 4 matrix. So you may want to go back there and check. So uh, we call it a tensor product, but you don't need to know tensors for that. Yes. Okay. Okay, now let's look at the other one where one is a pure state, but other is a not a pure state, right? So would they be correlated, right? So so if I have a trace of row square, right? We saw that it is row 1 times row 2. So I can multiply that. Remember that trace of row square, which is trace of um, row 1 tensor product row 2 um, uh, squared, right? Again, right? I can remove them into different products. Remember, we saw the properties of trace, yesterday. So we can just multiply those traces, trace of AB, right? So then both traces are one, right? So both I can get that. Sorry, in the previous case, both traces are one. So here I will always get trace of row square to be one in case of both being pure states. But if one is a pure state and another is a not pure state, for one state, let's say row 1 is a pure state, then this would be 1, but the second one is less than 1. So 1 multiplied by something less than 1 will always be less than 1. So the resulting mixture, if one of the states is not pure, is always not pure. It's a mixed state, right? Am I making sense? Or should I go back to the uh, thing, thumbnails? Maybe I can. I think we discussed the properties of trace yesterday somewhere. Um, yeah. So it is in these slides somewhere hidden. But if you have one in one non-pure state, then basically you would end up getting that as a totally non-pure state because one of the states has a trace of row square to be less than 1. Are you following me? Okay.
Professor, how do we know that the system is uncorrelated?
Somebody has a question, but I could not hear it. Can you speak
Uh,
loudly, please?
how do we know that it is a uncorrelated system? Like we get the row is in mixed state, but how do we know that it's uncorrelated? By experiment, you mean?
No, so when we say uncorrelated, that means that I can express it as a direct tensor product like this. If I can express it like a separate product where I have row 1 and row 2, two subsystems, then it is uncorrelated. If it is correlated, then I will not be able to express it.
Okay,
So
okay,
if I can express it like row is row 1 times row 2, then it is uncorrelated. For example, if I take, let us say row 1 is 5, 5, right? Row 2 is psi, right? Then if I take the tensor product, my row would be phi, phi, right? Tensor product with psi, right? Now I can write this, I can get the same tensor product by taking, let us say, some other state that is phi, big phi, which I would define, okay, I'm blocking it. So if I take this to be some state like this, then I can express rho as this, right? So if I can express it like that, then I'm able to separate them. If I express these, as a separate states that I can separate them, then that means they're not related. That whatever I measure on one is not related to two. That is, I can do if I want expectation value of some operator R, right? That belongs to particle one. then I can do that as trace over subsystem 2, right? With rho times R, right? Then that means that they are uncorrelated. I can just sum over the second subsystem and get the probability. So as long as you can express like this, if you can separate them like that, then they are not correlated. Are you able to see that?
Yeah, yes, yes, Professor.
If they are correlated, then this will not be possible. Okay, so here, so if you have we can have, if we have both particles as non-pure, if you have at least one of them as non-pure, the total trace will be 1. So always you get a non-pure state, right? So here, if I have two states that are mixed, right, I can build two states from two states that are mixed. I can build a non-correlated state. That is, I can make sure that I can express as this rho 1, rho 2. But if I have a state like this, right, that I cannot express as rho 1 times rho 2, then we would call that is not factorizable. That cannot be non-fact. So here this is factorization. Rho 1 times rho 2 is factorization. So if I cannot factorize it, then basically that's what I'm calling as correlation, right? Then in that case, we would say that we have a state that is not correlated, right? So for example, if I have this kind of a state, I cannot express it as a product of two states. Like you see the state vector here, I cannot express this state vector as a product of two states, unlike the previous ones. So one is spin up, another is spin down. So I cannot express that as a product of two different states. So when I cannot express, when it cannot be factored, that's what we call as correlation. So going back to the table, when I have two pure states, because the trace of rho square for pure states is 1, the total trace is 1. So they're always uncorrelated. I can express them as product, right? Only when I have two non-pure states, I can build a correlated state that cannot be factorized. If I have pure state and non-pure state, then I always can build a state that can be factorized into two different products. So if I can factorize, then it is not correlated. That's what we are saying, right? So for example, like if you look at uh, the here. So only when rho can be expressed as this, the total state is fixed by partials, it is uncorrelated. If you have uh, a state that cannot be expressed like this, then we say uh, is correlated. And like we can express, for example, here we can think of multiple spins. Let's say I have n particles. I have spins up along all the particles. Then you would think that, okay, if I have spin up z along all particles, they look like a highly correlated sets because I have every spin to be up, right? But that is not really the correlation because I can express it as a product. The density matrices I can express as a product as rho 1, rho 2 till rho n. So it is uncorrelated, right? So what we do is we define correlation by fluctuations in observables. We make measurements on, let's say we have two particles, we make statistical observations. And if those statistical observations are correlated, then that's when we say that there are fluctuations, right? Without any variability, fluctuation is undefined, right? So if you have fluctuations, but they remain uncorrelated, that means you can express them as a product state. So going back to whether a state is correlated or not, the basic thing to think about is if you can express the state as rho 1 product rho 2, it is uncorrelated. If you cannot express this as this, then it is correlated. That's the drive home message. And if it is correlated, that means there is entanglement. Am I making sense? Any questions? Okay, no questions. Okay, let us see briefly how we can what an entanglement pair means, right? So let's take this experiment where you have some sort of a particle in the center, some source. This source can emit kind of a pair of particles that have equal and opposite momentum. That means that it can emit in any random direction. So for example, if I say I have this source, this is the source. Whenever it emits to a pair of particles. It can emit in this direction, it can emit in this direction, it can emit in this direction, whichever direction. It emits in all directions. But whenever it emits, for example, this is Ka and this is Kb, then these are equal and opposite, meaning Kb is minus Ka, right? If this is Ka prime and Kb prime, then it is Kb prime is minus Ka prime. It's always equal and opposite. It can emit in any direction, right? But then I enclose this in a box. And then I cut out only slits on one side. I cut out the slits only on one side, right? So I enclose this in a box and I cut out slits only on this side of the box and the other side of the box, not in top and bottom. So suppose there are particles emitted like this, they won't make it out, right? These particles that are emitted that way, they won't make it out, right? Only like certain particles that would come through this slit, only certain angles would make it out, right? So now I get these particles out, right? The thing is that whenever they are emitted, they have equal and opposite momenta. I have mirrors here. And so this is my state preparation. So I'm taking some radioactive source that is decaying into a pair of particles that are emitted in equal and opposite directions, right? There are several such sources, right? And so you can just basically get them from two different sides, and I have mirrors to reflect them. And so I get some particles here. So this is my state preparation procedure. Now let us say I put some detector here on the left side and I measure something, right? I measure some momentum. So when I say measure, I make measurements on multiple things. So I'm getting particles, I'm waiting here. I make one measurement, I see the momentum is some value. I make another measurement, I see momentum is another value, not on the same particle. Whatever particle is coming out, I'm making measurements. So I make like, let's say 1,000 measurements on this side and 1,000 measurements on the other side. Then I would find that, for example, on this side, if I found 200 times spin is up, on the other side, 200 times the spin is down. If I find 800 times spin is up, spin is down, on the other side, I would find 800 times spin is down. So those are correlated. And the reason is that if I found that, if I measured here some particle, right, that let's say is Kb, that is coming from the bottom mirror, then what I would have measured here is something that should have come from the top mirror. Because when the source emits, it emits in equal and opposite directions. Are you able to follow that? What about the case when after certain reflections, they also come out? I'm not sure I understood your question, Priyanshu. Can you please elaborate? That's about the box, maybe, okay. What about the case when after other particles? Um, I'm not sure other particles, what do you mean by other particles? Like you mean to say the source is emitting other particles? Yeah, so we are measuring here. So usually this like if you have like a decay, right? It emits like a, let's say a singlet state of electrons, right? That are getting emitted in opposite direction or some singlet pair. So those are the only particles it is emitting. So it is emitting electrons from a singlet state that are going in two directions or like some other particles. So we are not considering distinguishable particles. We're only considering indistinguishable particles. So whatever particles that are coming out, it is the same particle, the same kind of particle. So it is not distinguishable. So it could be a one electron from singlet pair that is going up, another electron from the singlet pair that is going down. So both are electrons. It is not that we have electron and positron. Does that make sense? Yes, we are calling the correlations as entangled, Subhanshu. Yes, Shafna, that's right. So I don't say it gives you percentage of entanglement, but if they are correlated, that means that we cannot express them as a product state. So for example, now you look at the state that is written here, 1 over square root 2, Ka, Kb plus Ka prime, Kb prime, right? I cannot express the state as some phi1 product phi2. Try to express it as a direct product of phi1 times phi2. You will not be able to express that, right? So that means that they are correlated. So correlated and entangled are the same, but I like to use the term correlation rather than entanglement. The reason is because how do we measure the degree up to which observables are correlated? By making multiple measurements. So there are two things here. Again, one thing is that when we are measuring, when we say correlation, correlations are always statistical. Entanglement, the problem is gives you some sort of a non-physical description. Like if I separate two particles, I measure the spin of this from singlet to be spin up here. Somewhere the other particle on the moon is suddenly becoming spin down. So information is traveling faster than light. So that kind of confusion comes into picture, but that is not really true. The correlation, if you look at all the papers, the Nobel Prize that Alan Aspect, Zellinger, all these papers, they are actually statistical correlations that they're measuring. They're not actually doing this one single photon. They're doing single photon experiment, but statistics on single photon experiment on identically prepared systems. So whenever we talk about measuring the state, we're measuring multiple identically prepared systems, and we're looking at the correlations in statistical outcomes, right? Not in single measurements. So that's why we call it as correlation is a better word than entangled. But yeah, they mean the same things. And the way we measure the degree up to which the observables are correlated is, like I said, you keep measuring, right? For example, you put let us say let us say I have this box, right? The slits cut out, right? I can set up a Stern Gerlach along z direction here, right? And I can set up Stern Gerlach along whatever up or down, right? Uh, let us say yeah, so maybe like up and maybe like down, right? So if I or let's just say I set up just Stern Gerlach. Doesn't make sense to just let's say along z direction, Stern Gerlach along z direction, right? So if I measure like let's say 1,000 particles on either side, 1,000 particles on either side. Let's say 200 particles I found spin up. On the left hand side, 800 particles I found spin down, right? And on this side, 200 times I found spin down, 800 times I found spin up, right? Then I would say that these are correlated in the sense that 200 times whatever, whenever this is spin up, then this is showing spin down. This is spin down, this is showing spin up, right? So that sort of a correlation is what we are talking about. That we make multiple measurement and the percentage, there must be some parameter that describes it degree. I'm not sure. Degree of correlation, you mean? Yes, you could set up like along the degree of correlation by setting up along another axis, like instead of z-axis, you can set up along some other, let us say instead of z-axis, you could put along some theta, some other axis. That's what the Bell's theorem tells. And the degree of correlation is related to that angle theta. I hope that answers your uh, so you can some parameter that measure correlation degree. Yes, I think you can come up with a correlation degree of correlation by sort of plotting the data that you would get, right? So that's what I was trying to show here. Trace of a density matrix, some parameter like that. Yes, we will come to that. So so that is what is here, the degree of correlation, if that's what you're asking. So let's say I can write the total wave function. If I write in the position space, if you ignore the normalization, right, I can write the total wave function as Ka, Kb, right? Then I can write the probability density as 1 plus cosine of this. So I guess this is what you want to talk of as degree of correlations, right? So it would depend upon this cosine of difference between Ka minus Ka prime and Kb minus Kb prime, right? Does that answer your question? Priyanshu? Okay, that's okay. We can get back to that then. So basically what it means is that you are going to find the total probability density is going to have some sort of an interference pattern and doesn't look like subsystems. So, if I find, if I detect both particles in coincidence near a particular x2, then I would get these kind of cosine variations in whatever I'm measuring. So if we detect only one particle, then there is no feature, right? Because then that would be featureless. There is no, we're integrating over x2. It would not look like a feature. But if we detect both particles, then we do get some features, right? So if we detect only one particle, its distribution is featureless. Um, Again, if you detect only particle 2, then there is no interference. But you detect both, then you see that there are correlations between those two things. Those correlations are what we are calling as entanglement. So if you can express the density matrices as separable products, then they're uncorrelated, right? And entangled states or correlated states are uh, partially mixed states that you cannot separate them into these kind of factorized products. But if you make measurements on both sides, those measurements will look like they are correlated, right? So here we have an example that you could see. For example, if I prepare a 2-qubit state, right? Let's say it looks like this. What do you think? Is this state? So for example, here it is 0 and 1, 0 and 1, 1, 0, 1, 1. So it is 2 qubits that I'm preparing like this. And the question I'm going to ask is, do you know whether this is a uh, 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 product state or an entangled state? Do you think this is an entangled state? Right. It is not an entangled state because I can factorize it like this. So I can make it into 0 minus 1 or 0 plus 1. And so I would get 0, 0, 0, 1, 1, 0, 1, 1, right? So I can factorize this state that looks like this into two different states. So then we say that such a state is not entangled. So whenever I can write like this product state, that means they are not correlated. Okay, good. But if we have a Bell state like this, that is, I have 0, 0 or 1, 1, then I cannot express these as a product state. So another way to look at this is I would encourage you to derive the density matrices for these states, right? For example, you can derive the density matrix for this 5 plus state. Take the 5 plus, these are called Bell states in honor of John Bell, right? And you can look at what the trace of rho square would be, and you can see, try to express these like product state phi and x. It is not possible to express these states as product of phi and x, right? So so those we would say are maximally entangled states or maximally correlated states, meaning that if I measure particle 1 to be 0, particle 2 must be 0 because there is no other way, right? Are you able to follow me? So I would get these correlations. That's what I mean by correlations, that in the previous case here, if I measure particle 1 to be in 0 state, then I have a probability of measuring the second particle to be in 0, 1. So I can get 1 or 0. Are you able to see that? There are those possibilities. Like if I measure only particle 1, right, to be in 0, then it is possible that the particle could be from 0 or 1, right? So if I measure the second particle, let us say to be in 0th state, then I cannot quite tell whether that is coming from this part. Okay, you are not able to see the mouse cursor, I guess. Are you able to see my cursor? Okay. If it is correlated in one state, say spins, does that necessarily mean it's correlated in other states too? Again, you are using the word state in an incorrect way, Shafna. So you mean to say if it is correlated in one observable, say spin, then because state, yes. Not state. So we do not know. We do not know whether if one observable is correlated, we do not know whether all the observables are correlated. We cannot say that, but it is likely that uh, you could have correlations, but I don't know if it is a necessary that all observables are correlated, because I could measure, for example, energy of particles, right? I might get the same energy, but it may be like correlated in some other observables, right? So, but the point I was trying to make here is when we have a state like this, psi, if I measure, let's say I have 0, 0 plus I by 2, 0, 1, minus 1 by 2, 1, 0, minus I by 2, 1, 1, right? Then let us say I make measurement on particle 1. I make a measurement on particle 1, right? That is particles, let us say, that are coming out on left side, right? I make, let's say, 1,000 measurements, right? And I find 800 times it is in 0, right? And 200 times I find that it is in 1, right? Then I measure particle 2, right? Now, when I get this to be in 0 here, right, then I could get the second particle to be either 0 or 1, because the states are, I have states such as 0, 0 or 0, 1, which means that when I'm measuring first particle to be in 0th state, I could measure the second particle to be in either 0 state or 1 state. So I do not know whether my state preparation, whether the second particle I'm measuring is from here or from there, right? So I could get from either one. So I cannot exactly tell that, that this is correlated, because it could come from, this state 0, 1. If I measure 1 here, that could come from 0, 1 instead of something else. But if I have a state like the Bell state, if you look at the Bell state, if I have a state like this, 1 over square root 2, 0, 0 plus 1, 1. Now, if I measure particle 1, if I find particle 1 to be in 0, and I find particle 2 also to be in 0, then it must have come from only this state. There is no other way. Are you able to see that? If I measure this to be in 1, then, and I get this also to be in 1, it must have come from only this. There is no other way, right? Because there is no other state. But in the previous example, I cannot see, whether whether if I measure this to be in 0 and I find the other one to be 0, it could come from this, right? It could come from 1, 0. The second particle could be 0 because it is coming from another state preparation, right? Are you with me? Are you able to see the difference between correlation and not correlation? Any questions? Okay. Okay, so these are the 4 states that we would call as the Bell basis, right? So these are just 4 different states that are maximally entangled. So you can check that out using the density matrices if you want, right? We also have, for 3 qubit, there are entangled states like one is GHZ. So I don't remember G and H names, but Z I think is Ellinger. But 3 scientist names, I think. These are 3 qubit states. For Bell qubit states, those are 2 qubit states, right? So we have these 3 qubit states, right? And then these are also entangled, meaning that you cannot express them as products. That is, if you make multiple measurements, you will find correlations. So in the code that I provided yesterday, I showed how you can generate these states. We will actually try to run them on the quantum computer and try to see correlations. That's what I want to do, but not yet. Maybe in the next week we will do. But for this thing, you can try to run them on the simulated computer. So you can make measurements on 0th particle 1,000 times, right? And the first particle 1,000 times in Bell state, and try to see if there are correlations. So the code, I think, is somewhere in this here. Let's see, thumbnails. So that's just a simulated version of the experiment, Bell's experiment, but you will find correlations there. One of these things should have. I'm not going to run it now, but I will encourage you to run it yourself, because I have to, I have a lot more things to cover. But yeah, so for example, here we generated the Bell states. So this is the Bell state, 0, 0, and 1, 0, 0, 0, and 1, 1. So what you could do is, or this is a, excuse me, ZHZ state. So what you could do is you can go ahead and use the measure function like this, right? You can use measure, and you can do those multiple times. So you can put that in a loop. You can measure on qubit 0, and similarly you can do measure on qubit 1 multiple times, and then you see if they're correlated or not, right? And then you should be able to, this is again a simulated quantum computer, so it should show you correlations. But then later on, we will try to access IBM quantum computer and try to run this on quantum qubit, try to generate one state like this and try to run on an actual quantum computer and try to see whether we are able to see that. The biggest challenge with that, doing with that, is that we don't get enough time to run these experiments on the IBM quantum computer unless we purchase the tokens. So we have limited tokens, and so I want to use those tokens for showing in the next week and not in this week. But I encourage you to run these by yourself on the simulated ones, maybe after we finish the class. So that's all I have with respect to the density matrices and entanglement states. So we can't play on quantum computer. We can play on quantum computer if you have money. So if you are willing to purchase the tokens from IBM quantum computer or QBraid, there are a lot of platforms that have their own quantum computers that will sell you time on their qubits. You can purchase those. IBM gives some free tokens, so you can go to IBM Cloud, create an account, and yeah, IBM moved to cloud since July. That's right. That's the problem. So you have to buy the tokens from QBraid or some other things, and then you can play on a quantum computer directly. So yes, you can, and they're not that expensive. Yes, on IBM, first 10 minutes is still free, but the problem, Saptagiri, is that you have to find the particular IBM computer that is free, right? When you try to call the token, what I have found is that it just in the back end, it tries to switch from, there's a list of IBM quantum computers, and you can see which one is a real quantum computer, and you can try to use that channel, and it would try like 5 times or 10 times and then say within that 10 minutes, okay, this quantum computer is busy, so we are going to just run on like some IBM simulated computer, and then that's not real quantum computer. But if you buy tokens, you can run on a single and multi-qubit one yet. Yeah, I have not really tried on cloud yet, so I am reserving the tokens just in case, like for the class. So we will try to run it on the cloud during the lectures next week, because there is hands-on in the course title. So we will try to run it on an actual quantum computer in the next lecture. Not next lecture, but next week, one of the lectures in the next week. But the coding part using Qiskit is the same, except you don't use the simulated quantum computer. So that's the answer. So I will stop here. If there are any questions, you can ask me. If there are no questions, we'll come back. And then in the next lecture, I want to cover transmon qubits in greater detail and actually talk about how do we build this qubit. What does this qubit mean? And what does it mean when we are running it on IBM quantum computer? What is actually happening, right? So that is the part that we will cover in the next lecture. So I'll stop here, and if there are any questions, I'm happy to take those. If there are no questions, then please feel free to come back and join us at 4:45. We will try, Priyanshu. If we are behind of our normal schedule, I will try to take. We will try to cover it. We will try to do that. Uh, but that won't be today. It will be maybe towards the end of October 10th. We'll try our best to run on the IBM quantum computer. The main thing that I'm concerned about is the tokens and getting accessibility. And I also have to see how the IBM cloud is going to work. So we will try to cover as much as possible. Is the discussion group alive yet? Yes, we can try small circuits. I'm pretty sure we can try small circuits. Um, uh, I don't know if the discussion group is born yet, Shafna. I think maybe if one of you can take initiative and if one of you can take initiative and send out an email for Discord, then other people can join. Maybe Shafna, why don't you do that? If you can take initiative and send out something, then everyone can join there, that Discord or somewhere. Okay, that's great. Thank you. So same code we can run on quantum computer. Yes, you can run same code. Yes, you have to make a minor change. That is, in the beginning when we install Qiskit, Subhanshu, after that, you have to give your account ID, the API token, and specify which IBM quantum computer you want to run on. Let's just pull it up, right? I can show you. So like we can go to IBM cloud. So you have these, so you see you have a list of these, right? All these are online. Are you able to see that? Right. So IBM Pittsburgh, IBM Fest, but you have to look at like these are all should be those things. So if you sign in, let me see. I don't think okay. Um, I'm sorry, I don't remember the password. So I have to log in from my computer. This is not my computer. So but if you log in, basically it will you can create an account. It will give you like 10 minutes of free time. So you can create an IBM cloud account, and then there are instructions on what you need to put in. So the code is exactly the same, but except wherever we are saying, like let us say we say simulated, we simulated somewhere. We have somewhere in here. Uh, maybe this okay. Not I don't think we are doing anything here. Maybe in the other code we have. Let's see. Plus. Yes. So here. So you see here, Subhanshu, this is we have sim a get backend. So here the backend, I am just putting a simulator, right? So what we will do is once you get the tokens, you will introduce your API, and instead of the AEM simulator, your backend will be either like IBM Pittsburgh or IBM Torino, Brisbane, whatever you want, right? You can put those, but the problem is you have to get free time, right? So you look here, there are pending jobs, right? So like for example, now if I put on IBM Fez, my pending job will be the ninth pending job. So it will not run immediately. That is a problem in doing it on live class. but we will try to show you the code so that you can run it and see for yourself. So, but if you pay, I think there is also another platform. This is only IBM quantum computers, but you can also go to Cubraid. Cubraid. This one also has a quantum computing platform, and then they also give you like so you can see the pricing here. Right. So this is only giving you CPUs. So yeah, so if you want the superconducting quantum computer, this is 84 qubits, this much plus this, you pay and then you will get the API tokens and then it will give you what you need to insert. So instead of doing the simulate backend, you will put in whatever they are giving you. They will give you the API token that you will add and then exactly it will run the same. Does that answer your question, Subhanshu? Okay. Yeah. So we will try to run. I think I have so there are different quantum computers here. You can run it on trapped ion, neutral atom, and these are the simulators, right? And so these you can read about these more. But I think I have I bought some Cubraid tokens. So we'll try to use those tokens from Cubraid. The unfortunate thing is that I saw that after 1 month they expire. So if you like, it is crazy. Like I thought I bought and I will use them later, but they expired or whatever happened to that. So but we'll try to buy again and try to run some tasks. But the only thing is I cannot guarantee whether it will run when we are doing it. But we'll try to write the code so you can run it later on. So, okay, we'll stop here and come back after let's say 4:50. 4:50, we'll see you. Thank you. Bye.